Okay, so we talked about the wind-driven currents, which we just described them, but they actually have names, and some names are rather intuitive. This is called the Pacific North Equatorial Current going this way, Pacific South Equatorial Current going this way, but some names are not so intuitive. This is called Kuroshio, which in Japanese means black current, and there is a reason why it's called so. It's called a Gulf current or Gulf Stream over here, with Florida current, Caribbean current, Brazilian current, and there is the Somali current, the Agulhas current, and so on and so forth. Can you remember all the names? Well, if you're old enough to want to learn this, then I have a whole course on oceanography which is very basic on my channel that you can follow up on. Okay, so let's move to the other kind of current, where there are some places in the world where there is so much evaporation happening that the ocean is cooling and getting more and more salty, because evaporation leaves salt behind, which means it's like adding salt in a beaker and making the water heavier and heavier. So in the so-called Greenland, Iceland and Norwegian seas, or Jin seas here, ocean is losing heat, so heat is released to the atmosphere through evaporation. And here in the Labrador Sea as well, the heat is lost from the ocean and gained by the air, so heat is released to the air, which means ocean is cooling down, getting saltier, and waters are sinking. So these blue arrows show that the sinking water goes to the depth and then goes south and then goes into the Southern Ocean, and it gets warmer or changes its salinity, salt and temperature, goes into the Indian Ocean and comes back, goes into the Pacific Ocean and comes back. There are also places in the Southern Ocean, which remember is like a channel, also loses heat and produces some of the heaviest waters. All these waters that sink have names associated with them. These waters are called North Atlantic deep water because they sink deep. Here you produce water that is of different densities. One that sinks to the bottom is very heavy. It's called Antarctic bottom water, and there is water that's not so heavy that doesn't sink all the way to the bottom. It's called Antarctic intermediate water. Okay, so that water is mixing with the warm waters near the surface, right? So there is always mixing happening. We said this before. Why is the mixing happening? Because there is gravitational pull on the oceans on Earth from the moon and from the sun, which are creating the tides, and the ocean is going back and forth. If you go to the coast when there is high tide, you get the splashes of water, or the water comes very close to the beach, and when it's low tide, water goes far away from the beach, and so on. So all that mixing tends to mix cold heavy water with lighter upper water, and you get this circulation going on of water sinking and waters rising. This is called thermohaline circulation. Why is it called thermohaline circulation as opposed to wind-driven circulation or wind circulation, where winds are just dragging the ocean around? Here temperature change, which is thermo, and haline means salt changes. So when you change temperature and salt, what do you change? You change the density of the ocean water. So density changes are causing water to sink or to rise, and this vertical circulation and horizontal circulation together is called thermohaline circulation. It is also called the global conveyor belt. What is a conveyor belt? If you've been to the airport, sometimes when you are waiting for your bags, the bags are coming out of a chute where they are loading it outside from the aircraft. It's coming and falling and it's going round and round. That's the conveyor belt. So water is sinking and rising and coming back to the place where it's sinking. This is called a conveyor belt. So global conveyor belt. One other thing you should now try to connect here. We said before, when we looked at where all the energy we are trapping by increasing the greenhouse gases is going, we said 91% of that is going into the ocean. How is it going into the ocean? Of course, you can keep warming the ocean as the air gets warmer. You can imagine the ocean may get warmer, and it also sinks. The atmosphere can keep on giving heat to the ocean, and the water can sink and take it away. So there are places where ocean is able to take away the heat from the surface and manages to take away 91% of the energy that we are trapping by increasing greenhouse gases with our fossil fuels. What does it mean? That means ocean is also exchanging carbon dioxide and methane and N2O and oxygen and nitrogen and everything from the atmosphere. Carbon dioxide dissolves very easily, but not everything dissolves as easily. And those waters are also sinking, so ocean is also taking carbon dioxide with it and takes up quite a bit of the carbon dioxide that we are increasing by fossil fuel burning. Okay? Another trivia that you can add here is that the water that sinks several kilometers deep and keeps going around takes hundreds, if not thousands of years to come back to the surface and come back to where it sank. Imagine that. Okay? If you go to the North Pacific, the water is sinking here, and it is circulating around and coming to this region here, which is the North Pacific Ocean. That water has not seen, if you go to the bottom of the Pacific Ocean and take the sample of water, that water has not seen the surface for hundreds of years, because it sank somewhere and it's been circulating, and by the time it reached here, it is several hundred years. How do we know that? That's the detective work again. There are certain isotopes which sink when the water sinks, and they have a signature of the atmosphere, and once they sink and keep going, isotopes, what do? If you don't know, don't worry, but those who know, isotopes tend to decay. Some of them decay. So there is one isotope called carbon 14 which is being produced in the atmosphere. When it sinks away from the atmosphere, it begins to decay. By the time it gets to here, it has decayed a lot. So if you can measure the water, go collect that sample and measure how much C14 there is. When it decays, it converts back to nitrogen or another type of carbon, right? So let's not go into those details. You can measure the decay, and you know how long it takes for it to decay, and then you can say how old that water is, which means when was the last time it saw the atmosphere. Gets a bit complicated, but just think about the exciting detective work that is being done. And someday, if you learn your chemistry, and if you learn to go on the ocean with the ships, and or use robots to go and get the water and do the lab work to measure C14 and its decay rate and so on, you can be the detective who is going to say how old that water is and whether it's getting, its age is changing because of global warming. Because we said, because of global warming, surface temperatures are changing, winds are changing, evaporation, precipitation, everything changes, which means, is this circulation also changing? Of course it is changing, which means the age of the water will also be changing. So you can be the detective to go and figure all these things. Okay, so we'll come back and look at some cute animations from NASA and NOAA to understand how these currents are moving around, just to reinforce the concepts that you just picked up. So ocean has currents forced by the atmospheric winds, and also either gaining heat from the atmosphere or losing heat to the atmosphere, and hence changing its density near the surface. There are other ways to change the density as well, by forming sea ice, for example. If it gets very cold over the ocean can lose lots of heat and begin to freeze. And when it freezes, again, it rejects all the salts. The water molecules arrange in such a way that sea ice forms. It puts out all the salt, which means the water below gets salt, gets heavier and sinks, and circulation begins. Right? What happens to water when it freezes? This you have learned in school. It becomes lighter. Right? Hence, sea ice floats. You know that sea ice and glaciers float because you have probably seen it in movies. Maybe you have seen it in a movie called The Titanic, where a big ship went into the ocean, suddenly came into a glacier, crashed into it, damaged itself very badly, and sank to the bottom of the ocean and killed a lot of people. But it left a lot of stories, enough stories to make multiple movies. If you haven't seen it, ask your parents or siblings. Maybe they can allow you to see it, or maybe you can read about it. And there are people who go into the ocean and find out where this ship sank. They found it and they've been photographing it, and so on and so forth. The ocean has lots of secrets buried deep inside because of things sinking, water sinking, and so on and so forth. Okay, so that's the ocean. The main thing to also remember is that it's taking up so much of the energy and carbon dioxide and greenhouse gases, as we mentioned before. Because the ocean is keeping all that energy inside, the atmosphere is not warming as fast as it could. How much has it warmed? You should go and figure it out. Since about 1850, the global atmosphere is warmed by about 1.2 or 1.3 degrees centigrade. Okay, that's a lot of heat. You can imagine, if you take 1.2 degrees of heat into the ocean, you can compute how much energy that is. Tremendous amount of energy is being locked up in the ocean, which can be bad news because it's not going to space as thermal energy. It is in the ocean, which means it is in the Earth system, which means it may come back out someday, right? Which means it can begin to warm the atmosphere again, melt the glaciers, and when the water warms, it expands, which means sea level rises. So if you are near the coast and sea level rises, then water will come onto the coast, and when the storms come, more water will come on the coast, and so on and so forth. So ocean has a big role in controlling climate change, and how much water is coming, how many storms are forming, how energetic are the storms, how much water the storms will bring in, and so on and so forth. Okay, so ocean's role in climate is very important. If you are old enough, I have a full course on ocean's role in climate change that you can follow up with. Okay, see you with few animations in the next podcast then, kids. Okay, bye bye.